Hello, and in this video we're going to finish talking about the exponential models. This one we're going to do exponential decay base E. So the model is very similar to growth, and it's the same model. This value is the same. The equation is the same for base E decay as it is growth. The only difference between the two formulas is the value of K. So if the K value is going to be negative. Alright, so that's the difference in the value. If it's growth, K is positive. If it's decay, K is negative in this formula. Alright, so we're going to work some problems out from your worksheet that you had in your documents folder. Here's to the two examples that follow this formula on your worksheet. This one says radioactive decay. The half-life of radioactive carbon-14 is about 5,600 years. That means it takes 5,600 years for half of the initial amount to decay. Write a function in the form A equals A sub 0 e to the kt that models the decay of a 100-gram sample of carbon-14. Alright, so in this case we would need to figure out our decay rate. We know the half-life, meaning that we can figure out, we'll know A sub 0 and A temporarily while we figure out the decay rate. So in this case we have, we can do this with any amount we want. We're going to have half of it left over if we just put one amount in there. And then we know that K, we don't know what the rate is, but we know it takes 5,600 years to get to that half amount. Now we could have used the 150 here, put 100 here and 50 here, but when we divide we're going to get the same ratio here. So it's going to be a 1/2 to 1 ratio no matter what we do. So in this problem I'm just going to use a 1/2 for a half-life. This always works. Just like doubling, we can use 2 and 1 for doubling in the previous example when we do growth. Alright, so in this solving I need to take the ln of both sides, because in this case I would want to use the function that's the inverse of E. So these are inverses again, so we're just going to get 5,600K equals ln of 1/2. So we're going to take the ln of 1/2 and divide it by 5,600 to get K. Alright, I'm going to do that on a calculator. It's going to be a very small number. Ln 0.5 divided by 5,600. And it gave it to me in scientific notation even. This got an E with a little -4. So that's scientific notation. That means move the decimal 4 places to the left. So my K value, if I move it back 4 places, is going to have 3 zeros in front of it. It's going to be negative 0.0001 2377 123776 23776. We kept a lot of decimal places there for K. Alright, so that's the K value. It's a very small number. Its growth rate is way less than 1%. It's 1/100th of a percent decaying at a rate. So this is 1% right here. This is 1/10th, and this is 100th. So 100th of a percent if we move the decimal over 2 places to make it a percent. Alright, so then our equation here would be A equals 100, because that's our starting value, e to the negative 0.0001237776 t. This is our equation that models the amount of carbon-14 in a radioactive substance, or basically in an item that's been fossilized. Basically we can identify the carbon-14 in a fossilized object and determine how old it is. All right, so we got some carbon dating here. On the second example, we have the formula now. We want to figure out something about probably how much time it took before how old the item is that we're looking at. So in example 5, it says carbon dating some organic material was found in an ancient fire pit, and it was found to contain 65% of the carbon-14 found in living organisms. Use the above model to estimate the age of the fire pit. So if it had 65%, we would need to take 65% of 100 grams, because that's how many, that's what we have. We have 65% of a 100-gram thing. So we need to know that so we can put that in for A. To start off with, we're trying to find T in this formula. We want to figure out how much is in our sample, how much carbon-14. It says 65%. It doesn't give us an amount, so we have to take 65% of our initial amount. And in that case, that's 0.65 times 100, which is just 65. So that means we have 65 grams of carbon-14 in our thing. Now, it wouldn't be 65 if this wasn't 100. If this was some other number, we'd get some other value. So in this case, we're going to use 65 equals 100 e to the negative 0.000123776 t. All right, now what did I did with 1/2 up here for half-life? I'm going to get the same thing when I do this one. I could have probably just started off with 65% here. If I divide by 100 here, I get the decimal for 65%, and that always occurs when they're giving you a rate like this. So I'm going to get 0.65 equals e to the negative 0.000123776 t. Now we could probably round to the lower decimals, but we just need to I want to keep it as accurate as possible, so I'm keeping a few more decimals than I might usually do. So ln on both sides. In the solving process, we want to get rid of that e, so we're going to use the opposite or the inverse function. I'll remember this decimal and keep writing it down. So in here, we have the inverse here. That's going to give us negative the decimal 123.776 t equals ln 0.65. So we just need to do the division to figure out how long it took to get to 65%. Now, since my calculator already had this number in it, I can just use that in the process of doing this. Now I just have to take ln of 0.65 and divide it by my answer. That's second, this negative symbol, so I get my answer, because that's what decimal was in there. So I'm holding the whole decimal in there, and I'm dividing by it, so I don't have to type it in again. I do that, I get approximately 3,480 years. So 3,480 years to lose 35% of your carbon-14 in an organic material. So we're assuming that that's over 3,000 years old, close to 3,400 years old, this organic material that they found by using this radioactive half-life. All right, so this is an example of exponential decay. Now, we can do several different types of examples. As long as we're looking and using a continuous decay rate, we would use this formula. If we have a decay rate that's based upon a time increment, we use the previous example, base B. So in this case, we're doing continuous because we want to think about years, minutes, seconds. How long would it take continuously? So that's why we're using this formula in these two types of problems. And remember, the only difference between base E decay and base E growth is this value right here. K is either positive or negative. In this case, negative. In the growth, it's positive. All right. And that's my last example on exponential models, decay versus growth, base E versus base B.